Okay, we'll have a look at now calculating the azimuth for a star. We're going to look at the star Vega, example 3. We're told the day, October the 2nd, we're given a time GMT, latitude and longitude, the bearing by compass and gyro of Vega. So we need to find the true azimuth, and once we've got that we can find the compass error, deviation and the gyro error. Now with a star, well, we're given GMT, so we can go straight in the tables and we look up the GHA for Aries. Okay, so it's on the 2nd and we need the GHA for Aries at 20 hours, and it's 20 hours 00 minutes, so it's just straight 20 hours. So we write that down, 311.25.2. Now there's no increments because it's 0 hours. So it's just 20 hours and 0 minutes, so we've no increments. So we've now got our GHA of Aries. Now we apply our longitude, and our longitude is 4 degrees 21 east. So longitude east, Greenwich is least, so we add it. Therefore our LHA of Aries is 315.46.2. Now we need to find our LHA of Vega, so we always now apply the SHA of Vega and we add that to Aries, the LHA of Aries, to get our LHA of Vega. And we get the value for the SHA from the column at the side on the page. On each page, but we're using the page October the 1st, 2nd and 3rd. We go down to the bottom to Vega and we find that the SHA is 8 degrees 57.2, that's the sidereal hour angle, and the declination is north 38.46.2. There's no D correction for the stars because they're so far away you don't need to use the D correction. So we've written down the SHA 8 degrees 57.2. We've also written our declination down and we've decimalised that now to 38.8. So we find when we add these two together we get an LHA of Vega of 396.43.4. Well, obviously it can't be more than 360, so in this situation all you do is subtract 360 and it leaves us an LHA of Vega of 36 degrees 43.4. Again, we decimalised that. So we now go into the ABC tables. We're going to table A with the LHA and our latitude. We go into table B with our LHA and our declination, and we get our A and B values, and we find that A is south because of the latitude, because of the LHA, the value of the LHA. B is north because of the value of declination, of course it's always the same. C now is the difference between the two because one's north and one's south, and it's named the greater of the two. So C is 0.58 south. We then go into the tables with that C value and we find that we do a little bit of interpolation. We're going with latitude 55 degrees 12 and we find that our azimuth reads 71.7 degrees west. So we do a slight bit of interpolation required. So we have south because C is south and west because the LHA is less than 180 degrees. So whenever the LHA is less than 180, the final azimuth is always named west, southwest. So with south, 71.7 west. So I've done a little drawing here. We're going south, 71.7 degrees. Now, south is 180, as you know, so we're going towards the west, so that makes that 251.7 degrees true. 180 plus 71.7. From the information on the question, we're told that our compass bearing was 258 degrees. So the difference between the two is going to be our compass error. And we find that it's 6.3 and we name that west because compass is best. Now let's find our deviation. We know that variation and deviation together give compass error. Compass error is 6.3 degrees west. Variation, as we're told in the question, is 6 degrees west. So therefore our deviation must be 0.3 degrees west because these two here must equate to this, the compass error. So our deviation is 0.3 west. We're told that our gyro was 252 degrees gyro. Our true is 251.7. Therefore our gyro error must be 0.3 degrees and gyro is reading more than the true, so it must be a high error. So the error is high, 0.3 degrees high. So with the azimuth for a star, you just need to get the GHA of Aries, add the SHA for the star, that gives you your LHA for the star. Declination you just get from the tables, use the ABC, and now you can get your true azimuth. You could have also done that using the formulas that I mentioned in the previous example.